Today we are going to talk about meta-learning. So let me start with some motivation first and then dive into some technical formulations of meta-learning and current state-of-the-art methods for meta-learning. So in many applications, we don't have large training data sets. So we have talked about supervised learning. We have talked about unsupervised learning, like GANs, VAEs. We also talked about self-supervised learning, where we don't have access to the labeled data. But in some cases, we have just not many even labeled data sets. So that's basically the regime that we are going to think about it when the number of samples in our training set is small. But interestingly, if for humans, even with few samples, we can basically perform pretty well on some basic learning tasks, like, for example, image classification. So how humans can learn to adapt to new tasks with even very few examples, but current supervised models require a lot of training samples. That's basically going to be the caveat that we are going to talk about. So let me put it in writing. In many applications, we don't have a large training data set, but interestingly, humans can adapt and basically learn on the fly. So why is that? Why can we learn on the fly and adapt to a new task even with few training examples? Maybe, let me be a little bit more specific, just, to warm up. Let's look at one example to make sure that we are all on the same page. I'm not a really good artist. I'm not even like an okay artist. But let's say I have two types of drawings. My drawings in the morning. I have a good, night's sleep, so I'm happy. I have my coffee, so I'm drawing shapes like this, right? So there's this, there's maybe something like this. I have another drawing, maybe something like this. Okay, and maybe after a work day, I have some drawings in the evening. Maybe I have a very long day, and I draw stuff like this. Unique shapes. Okay, so these are the first column. They are my drawings in the morning. The second column, they are my drawings in the afternoon. And now this is my training set. And now I'm gonna give you guys one example in the test time to determine if this example is a drawing from a morning time or evening time drawing. Okay, are you guys ready? All right, so I have 6 examples in my training set, 3 per label. I have 2 labels. And in the test time, I give you 1 example. And I want to see if this example is more likely to be drawn by me in the morning or in the evening. So what do you guys think? So I have 2 votes. Maybe more of you can write up your responses in the chat box. Oh, amazing. Like almost everyone says it's like an evening drawing. That's amazing. And in fact, that's right. That's correct. That's an evening drawing. Okay, so look at this learning task, right? So I have a binary classification problem. I have 2 labels, and I have 3 examples per class. But humans, almost all of you, in fact, not almost, all of you could correctly predict the label in the test time with just few examples. So why is that the case? How come humans are really good in doing this task with very few examples? What are your thoughts? I cannot train a deep supervised model with just 3 examples per class and then expect it does well in the test time, right? Just a regular supervised model. Contextual learning, good. So basically 1 point is that, oh, like you're looking at the textures. You know, here the curves are in the morning drawings, the curves are smoother, you know, but here they're sharper. You know, we have edges, and that's the feature that you guys use in order to determine if it was a morning drawing or an evening drawing, right? But basically, we have a lot of prior knowledge, prior information about drawings, and we are using that prior information in addition to these few examples that we have in order to make a good prediction in the test time. Right? So the key here is to use prior knowledge or information in basically performing a new task. So we are not starting from scratch. So we are not starting from like knowing nothing about images, about shapes and stuff, and then, you know, trying to solve this classification problem. So we have all of the prior information in our brains, and when we look at examples in this particular task, then we can immediately use that prior information, maybe adapt it a little bit in order to make it tailored to this particular task. For example, looking at just smoothness or sharpness of the curves, and then use that adapted information in order to deal with this new task. So that's basically the key goal in meta learning. So basically the question is, how can we train AI ML models similarly to use basically prior information from solving other tasks in order to solve a task in hand more efficiently. So that's basically the key question that meta learning is trying to address. In other words, the goal of meta learning is to train a model, let's say, on different learning tasks such that it can solve new tasks using only a small number of training samples. So that's the whole goal that we want to accomplish in meta learning. So I'm going to train my model on different but related tasks, like for example, image classification, but not on a particular label. Right? So here the label is like my morning drawing, my evening drawing. Maybe I'm just going to train my my AI, my model on different classification tasks. For example, if it is like a painting or it's a sketch, if it is cats or dogs, like all of them are somehow related to each other. So, and the goal is that after we train the models, we are going to somehow extract out some prior knowledge from the training process on variety of tasks, and then using that knowledge hopefully will guide us in order to tackle the new task more efficiently. Okay, so that's basically the main goal of meta learning. So there's a question it asks, isn't it this kind of overlapping with transfer learning? Could you stress the difference? So it's a little bit of a, they're related for sure, but it's different, right? So in transfer learning, you're saying that I learn a model for a particular task with, potentially a lot of data, and to see if it, if I can use the model, in some other related tasks, and how, the model will perform in a new task. So here we are going to adapt, right? So it is related. So we are going to take that model, I haven't talked how we are going to deal with it. We're going to take it and see how we can adapt it in order to basically solve the new task more efficiently. All right, so let me be a little bit more specific about the type of problems that you're going to talk about. So obviously this goal is very general, so it doesn't have to be classification problem. You can basically apply it to any learning problem, reinforcement learning, so on and so forth. But here we are going to start with classification problem. And mainly, we are going to focus on few shot classification. By few shot, I mean we have few examples per label during training. All right, so let me introduce some notation. So as our input, always we are given some data set, right? So here we are going to give a data set that contains multiple smaller data sets. So the data set that we have is going to be referred to as meta train data set. So it has potentially an smaller train and test data set. So I have DI train and DI test, 1 to n. So each of these data sets, these are labeled samples. If, for example, if I want to look at my DI train, these are samples like XJs and YJs, labeled samples. How many samples I have? Let's say I have K samples in the training set of DI. And in the test set of DI, I also have some label samples just to do the evaluations. How many I have? Let's say I have K prime. That can be different than K, often smaller than K. Okay, so in each of these data sets, so we have a training data set. Maybe I give you 6 examples. 3, let's say I have a binary classification. I'm going to give you 3 examples per class, like the example that we started with. And I'm also going to give you some, test data, maybe, 2 examples per class. And the goal is to learn a model on the training portion in order to do well in the test portion. Right? So one main thing is that everything here is a part of my training. Remember, so in supervised learning, I have a training and a test. So in the test, I cannot use the test portion of my samples during the training. So here, it's a little bit of a complicated notation, but this is probably the best we can do. Is that in the training I have smaller data sets and I have access to both training and the test part of that data set. So that's a very important distinction compared to supervised setup. So each of them is also referred to, each of these train and test data set is also referred to as a task. So this is task I. Sometimes, in some literature, it is also referred to as episode I. If you read the paper and see it talks about episode I or task I, it means the ith small data set in my training. Okay, so that's basically the meta training data set. Okay, so one more terminology to finish the training part. So if I have K samples in the training portion of my smaller data sets, I'm going to call this a K shot classification problem. So K-shot classification problem in fact, so let me actually rephrase that. So K-shot classification means I have K samples per label. So if I have, say, dogs and cats, if I'm doing a binary classification, so I'm going to have K times the number of labels in terms of, the whole samples I have in individual training sets for a particular task. So that's a convention that people use. Some papers, they use K as the whole training, the size of whole training set. That's, also sometimes people use that. But here we are going to use K as the number of samples per label. And let's say then because I don't want this to be confused with this notation that I have, so let me call this smaller K. So it's a smaller K, it's a bigger K. So K is the number of training samples per label. And if I have L labels, let's say my Ys can be from 1 to L labels, it's going to be also referred to as L-way classification. So in the literature, for example, if you see people say, oh, I'm going to look at two-way 5-shot classification problem, it means in each of the individual tasks that I have, individual smaller data sets that I have, in the training portion, I have a binary classification. It's a two-way classification. And for each of the labels, I have 5 examples. And so that's the convention that we have. Okay, just to make sure we are on the same page. So what about this problem? How would you refer to this problem that we solved? Two-way 3-shot classification, exactly. So two-way because it's a binary classification. 3-shot, we have 3 examples per label. Great. It's a little bit confusing notation. It's a complicated notation, but when you get used to it, then it's somehow going to be burned in your brain. So you often don't even think about it. Okay, so that's given for me during the training. Right? So these are individual tasks. I have training test portions of individual smaller data sets that I have. So in the test time, so I'm going to be given some new tasks. Right? So that's basically the evaluation portion. New tasks in the test time. So it's called meta test. So I'm going to be given a data set like this, meta test. So it can potentially have multiple new tasks. It doesn't have to be one task. So and each task again is going to consist of a train portion and test portion. Okay. So the train portion again is a labeled data set. So I have XIs and YIs for this. Let's say I have K of them or some number of them. So why do I actually use J here? So let me be a little bit more consistent. Let me use I. And then the index will refer to the task. And then here would be J1 to K. Okay, now what is the goal here? The goal here is that I want to learn a function to quickly adapt to the test portion of to the train portion of a task in order to solve the task in the test part of the data set. Right? So I'm going to basically train that procedure in n tasks that I have during the training. I want to see, okay, so can I take these 6 examples and do a classification, and then let's see how I perform in the test time of that particular task, and I'm going to try to learn a good way of doing it. And in the test time, now I am given a training portion. Right now I have like maybe 3 examples per class in a binary classification, and I want to quickly adjust to this new small training set that I'm given in the test time. And then I'm going to evaluate it in the test portion. So the final evaluation is going to be done in the test portion. Okay, I know it's a little bit of a complicated setup if it is the first time you're seeing it. So let me just repeat the setup. So in the training part, we are given n tasks. By task, I mean we have a small training set and a small test set. So the goal is to learn a procedure in order to quickly adapt to the small training set that we are given in order to perform well in the test set. So remember, the labels, for example, in the classification can be different across different tasks. Maybe in one task, I can classify dogs versus cats. In the other one, I can classify elephants versus camels. So the tasks can be different, but in a way, they are also related to each other. All of them are image classifications. In the test time, now, let's say I learned that procedure. I have somehow extracted some good knowledge. I'm going to make it a little bit more concrete. And then the goal is that in the test time, I'm also giving a new task. A small portion of it is the training set. I want to quickly adjust and adapt to that part of the training part of the task and see how I perform in the test portion of it. Is this clear, and are there some questions? Can you go over what I and J's are for the test set in the meta train? Okay, so for each of these, I is the index of the task. Let's say task I, which is the smaller, test train portions of my meta train, and J is the index of the sample, because each of these data sets, they have maybe 3-5 examples. Right? So here in this example, it would be sample 1, sample 2, sample 3, but this whole thing is probably going to be my first train data set. And it's going to be the first sample in the train data set, second sample in the train data set, third sample in the train data set. Any other questions about the setup? So is the test set supposed to be J1 to K prime? Yeah, you potentially have different number of samples and you have. So here, for example, you have 3 samples per class or 6 samples altogether. And in the test time, you only have 1 sample, right, in this extreme case. So don't really worry about these, K prime notations. These are just like, some notations to refer to the number of samples in each training and test. And in fact, some good meta learners, they don't, use a fixed number of training examples in tasks, right? So you also want to say, oh, maybe for one task, I have 5 examples. For another task, I have like, maybe 2 examples. And for another task, I have like, 20 examples. So here we are just, I don't want to like, use very complicated notations, but in practice, the number of training samples per task can also be different, but we are not going to consider that.
Sorry, my question wasn't about the K prime. It says I equals 1 to K prime. So I was asking, is it supposed to be J equals 1?
Oh, absolutely. Yes. Thank you. Thank you very much.
Yeah. Sorry if that wasn't clear.
Yes. No, that was a test. You are awake. You got the point. Okay. So there's another question. Are there any rigorous ways for us to say that our tasks are related? Great question. So far, it is hand wavy, right? So most of the literature, it's also like a very growing and active area of research, and similar to the domain generalization, if you remember that we were talking about like how domains can be related to each other. it is not very clear, at least mathematically, what would be a rigorous and useful definition to say how tasks are related to each other. So because of that, in fact, we are going to mainly focus. So there are some, literature saying that, okay, so the tasks are coming from a distribution, right? And each time we are taking a sample from that distribution, but how useful those definitions are in practice, it is yet to be seen. So here in today's lecture, we are going to focus on classification. And by related tasks, we mean, let's say you take an ImageNet, it has 100 labels, but maybe in one task you classify 2 random labels. And because, they're all coming from a ImageNet classification, task distributions, they are somehow related to each other.
Yeah, thank you, Professor. If I could quickly add on something in the intuitive framework that you've created, a kind of meta learning that I think would be very interesting, that I think humans do, is being able to read about something and then take that learning from a different domain and apply it in here. Or maybe domain's not the right word, but that's why I was thinking maybe it wouldn't be in the best interest, or it's ill-posed to try to rigorously define a framework here.
Right. So I think that's a good question. And as I mentioned, there are some efforts in doing that, but, it's yet to be seen what would be a proper way of making it a little bit more rigorous. Okay. It should be J1 to K prime for the test set. How did I make it? J1 to K prime. I think I'm fine with these notations. Maybe there's like a mistake in one of the notations. You guys are, smart. You adapt. You adapt to my handwriting. So that's in fact a part of meta learning. Okay. The question is how to use the meta train to solve meta test tasks more efficiently. For example, using very few examples in the test time tasks. Okay, so there are different, you can think about it, to this problem from a Bayesian perspective, but since almost all of the practical methods, they use like point-wise estimations. And since we haven't talked about Bayesian deep learning at this point, so I'm going to start from a different angle. So we are going to use the meta train to learn some meta parameters that can be helpful in solving my tasks more efficiently. So let me put that in writing first. So we are going to use the meta train to learn meta parameters. Let's call them with theta. These are kind of, encoding my knowledge, right, about the meta training tasks that I'm solving, such that, okay, so I'm going to have a base learner. Let me call it with A. It can be an algorithm. So I'll talk about that in a minute. So if I apply my base learner to the training portion of a task, and I'm also given access to my meta parameters, theta. So A is a base learner. It can be different things, so I'm going to talk about that. It inputs the training portion, maybe that 6 samples that you have first example that we talked, plus some theta, which encode some information from previous tasks that we have solved. And then it's going to output some task-specific model parameters. So these are task-specific model parameters. And A, as I mentioned, is quote unquote a base learner. So I'm going to be more specific about it in a minute. So the goal is to use MetaTrain to learn meta parameters data such that if I have, you know, a base learner that inputs the train portion of a task plus theta and outputs like task specific model parameters, the model parameterized by phi I want that to be a good model for the test portion, right, of the task that I'm looking at. That's basically the key idea behind many meta training methods. You give me meta training sets, I'm going to learn some meta parameters data, such that in the test time, you give me some smaller number of samples as my training set. The base learner, it's going to take those smaller number of samples plus my prior knowledge that is encoded in theta, and going to spit out task-specific model parameters phi I, and we hope that phi I is good, is a good model for that particular task. Okay. Let me, based on this intuition, without being specific, so far I haven't been specific about this A, right? So just, you know, think about this A as a base learner. If we don't want to be specific about it, how would we train a meta learner in order to learn a good set of meta parameters data? So I'll just minimize the error of this procedure over tasks in my meta training data set, right? So that's basically the whole idea. So let's say I have, it's going to be my training procedure. So I have a loss function evaluated on the test portion using what? Using phi I, that specific model parameters for that, that is model parameter for that specific task. And maybe it's a cross entropy loss for the classification or hinge loss or whatever. What is phi I? Phi I comes from my learner that is applied to the training portion plus parameters theta. Theta encodes the input, the prior knowledge that I have, right? So I apply the learner to the training portion plus the parameters theta. I get like model specific parameters phi I, and I evaluate the loss of phi I on the test portion. And how many tasks I have? I have n of them. So I can repeat it and evaluate my average loss. So I'm gonna pick a theta that minimizes this loss function. And that's it. That's basically the training procedure for meta training. So you can see here phi I depends on theta. So the training and test the data sets are constant. So I can potentially solve this using gradient descent on theta. If this A, the learner, is differentiable and it's a nice function. So that's going to be my training procedure. Let's say I solve it. using gradient descent, I compute theta star. Now in the test time, I'm giving a new task. Remember, we are given one or multiple new tasks. Let's say for simplicity, I'm given a new task, one new task. Let's just call it without an index because it is just one, the train, the test. Now I'm going to apply my learner to the train portion, and with which theta? With theta star. Right, so that's basically the theta star that we computed. Then it's going to give me a specific model parameter for this task, and then evaluate quality of this model on the test portion and see how we perform. That's the training and test procedures for meta learning. Obviously, if you have multiple test time tasks, you just look at the average performance and see how you perform. Okay, are there questions?
Professor, could we maybe briefly go over, what this base learner is, and maybe I can see if my understanding is correct. But I'm guessing that it's essentially a network or something, and we ultimately want to look at the parameters of that network after, or?
Hold on that thought. So I'm going to talk about that next. So I haven't talked about it. So
great.
Yeah, there are questions about definition of A. I have intentionally made it abstract at this point, right? So, I like to think about, this problem from a little bit higher point of view, and then I'm going to be specific, right? So let's say A is a learner, and then that's going to be my procedure. This learner gets like theta, which is the meta parameters, plus your training set. It spits out a vector of your model parameters, phi I, and then you evaluate phi I on the test portion. Okay, so what are thetas? What are A's, right? So that's the key element of design for meta learning. So we have, in fact, different options for A. Okay, so one option is that A itself is an optimization-based learner. A itself is an optimization-based learner. And this is proposed by Chelsea Finn and co-authors in 2017. So the idea here is to train a model that can be easy to fine-tune on new tasks. You have seen, I think, a variation of it in previous lectures. It's basically, we are going to start, we are going to look into one-step fine-tuning. But you can do multiple steps as well. It doesn't have to be one step. One-step fine-tuning. So I want to have a theta that if I take one gradient step in the direction of a particular task, for a particular task, I look at the loss function of that theta, and obviously evaluated on the training portion of that task. I evaluate the gradient, go one step or potentially multiple steps of gradient. This gives me my model, my task specific parameters. Now here you see, this is my A. A inputs, remember, the training portion of a particular task plus theta, and spits out task-specific parameters phi I. Right, so that's basically an optimization-based A. And then I'm going to evaluate the model with parameters phi I on the test portion of my task. Right, so in that case, my optimization is going to become, I want to minimize over theta over all the tasks that I have. My loss function, remember, I am using task-specific parameters phi I on the test portion. And that is defined, phi I is defined as theta minus alpha times gradient theta di train. And here we have di test. So in other words, over many tasks, we want to learn a parameter theta that can quickly be fine-tuned to get task-specific parameters phi I. So this is called model agnostic meta learning. It's the name that they're given to this method, or MAML. It's really simple. Okay, now the question would be, you know, how you update it, right? We are going to use just gradient descent in order to optimize over theta. So what would be the gradient of this objective? So the gradient goes into the summation. So I'll have 1 to n. All right, now let's look at this loss function that we have here. So of course, I'll have the gradient of the loss, but I should look at the gradient of the inside, which is phi I with respect to theta. Right? So I have gradient of phi I with respect to theta times the gradient of the loss evaluated at phi I and di test. So that's basically the gradient of this objective function, and I optimize my theta based on that. But now if you look at phi I itself, it has a gradient term with respect to theta. So therefore, here we are going to have a second order derivative in order to compute the gradient of the objective with respect to theta. So I'm going to have second order derivatives here. And this can be expensive. Obviously, there are some techniques for Hessian vector product that make it a little bit more efficient. But in general, this step is expensive. The reason is that we need to solve it many times. Remember, we have multiple training tasks, so we need to solve this optimization many times. So this part is the expensive part, bottleneck part. So because of that, the authors, they also proposed a first order MAML the first order version of this. Okay, so let me pause and ask, in fact, you guys, how would you design a first order method for this meta-learning approach. Or if there are some other questions, I think it's a good time to ask. But I want to see your opinion. So we have this method, so it has like second order terms. In terms of the derivatives, what would be a proper way, of not dealing with second order derivatives? Can we approximate the Hessian by inspecting how gradients change? Perhaps. But then that can also be expensive itself, right? Because we need to solve it many times during training. This should be repeatedly done over multiple tasks. Okay, so let me just write it up because we don't have much time. Okay, so let me use another color, in fact. They just ignore the second order term. I'm gonna put 3 hands just to make sure that, to emphasize it is very hand wavy. What they do is basically replace it with identity, with the identity matrix. And surprisingly, at least on some particular data set, let's say on mini ImageNet, it's a data set that you just sample smaller tasks from the ImageNet. It works fine. So not much loss of from the performance, but of course, it is not a general way of doing it. In some tasks, the second derivatives are going to be important. So that's why I, put hand wavy emojis, here. So there are some other variants of this technique. For example, there's a method called reptile, proposed by Nicole et al. In 2018, very related to this way of updating, this way of solving the learning problem, but with some smaller differences. So for the interest of the time, I'm not going to go into the details, but you can take a look at those papers. Okay, so that was it about one way of characterizing the base learner in order to quickly adapt or meta parameters to a new task. There are some other suggestions about approximating the Hessian and stuff. I think all of them are good, but it may actually be expensive during training. So that's why they just ignored it and it worked okay. Remains to be seen if in many other tasks, this first order approximation is going to be good or not. There's a question, instead of model parameters, can we learn the optimizer parameters itself? Yeah, so there are actually some works, hopefully I'll be able to talk about them, but you can even learn hyperparameters of the model. So hold on to that thought. So if I talk about other ways of characterizing so that may answer your question. So that's one way to basically characterize Remember, step back. So that's why I started from like a high level, right? So what was A? A is a learning a base learner that takes the training portion plus theta and spits out my model specific, task specific parameters. So another way to quantify, to characterize A is to use a simple learning algorithm. So A can be, is a simple, maybe linear, or even non-parametric, like nearest neighbor learner on data embeddings computed via f theta, right? So in this way, theta would parameterize my embedder. I'm going to embed my samples in a space, and then A is going to act like a simple learning method that can in fact use very few examples and then provide like good labels for the tasks that we have. So there are many methods in this area. So I'll talk about two of them. Lee et al. In 2019, they basically use f theta. It's a neural network, is used to compute embeddings. Therefore, my common knowledge is the embeddings, right? Theta would parameterize the embedding function. And then A is going to be just a linear classifier. A linear classifier, for example, SVM. And that's it. That's basically, you plug that into a learning framework that I started with. And A, which is linear, it is, you can just write it down. You can compute the derivative of the objective function with respect to theta, and then optimize for model parameters. Let me see, I have 5 minutes left. Let me just add a quick note. I won't go into the details of this because I want to talk about another family. So instead of writing SVM in their primal form, if you have taken my 726, you can write SVM in the dual form. And the dual form has this advantage that the number of use dual form of SVM, in that case, the number of optimization variables is the number of training samples multiplied by the number of classes. And for few-shot classification problem, it's going to be small, right? So if you have 3 samples, 2 labels, then you have 6 optimization parameters. So that will make this whole procedure really efficient. And that's the whole point, because A is something that you're going to apply multiple times. So we want to make sure that we can, use it really efficiently. And that's the main idea of this paper. And as I mentioned, A can be a non-parametric learner. So in fact, did I put it here? So let me just add a separate item for that. A is a non-parametric learner, like nearest neighbors. Again, let's look at the case that with f theta we find embeddings. So we have embeddings of x using function f theta of x. And this paper by Snell et al. They are basically using like a clustering based loss in order to define A. So they define prototypes. Types. Okay. These are basically cluster centers. Let's say you are looking at the 5-shot classification problem. Basically, for each label, you have 5 samples. And you compute centers for the clusters using their embeddings. Okay, so this is going to be center 1. It's going to be center 2. So center K is computed just the average of your embeddings for that particular label. And then what is my A? What is the prediction? How I'm going to make my prediction? Then the probability of a particular label given a sample in the test time, they assume it is computed via this formula that I computed distance of the embeddings with a particular center assigned to that label. And if the distance is closer, it is more likely that my sample is going to be assigned to that label. And I normalize it over different labels. And this distance metric can be Euclidean, it can be cosine similarity, and I'll just use maximum likelihood in order to fit theta to my training set. So that's another way of characterizing A. And one last way, I know we are running a little bit behind. One last way is the case when A is just a black box, like RNN is black box. For example, an LSTM or RNN, which in fact we'll talk about it in more details next lecture. And in this case, the assumption is that I have a recurrent neural network parameterized by theta. This is my common knowledge. And it inputs my training samples. It's my first training sample. It's my second training sample, so on and so forth. And it outputs the specific parameters, model parameters for a specific task. And then I go and evaluate this on the test portion. Okay. So one disadvantage of this is that having a LSTM or a recurrent neural network to output all model parameters for a new task is not very scalable, and the optimization is difficult. There are a lot of techniques that they say, okay, maybe it doesn't output the entire set of parameters for a new task. Maybe it will just output maybe a portion of it that will be task specific, and some portion of it will be task agnostic, and that will make it a little bit more scalable. But in general, these methods are a little bit more difficult to train. Okay, so that's all I have for meta learning, and there are many other methods somehow falling in different categories that we described. As I mentioned, one issue of the optimization-based method is that the second derivative can be expensive. One issue about the non-parametric methods, they're usually harder to generalize for varying number of K, that the number of samples that we have for each label. And one issue of black box method is that usually the optimization that we use during the training can be a little bit more difficult. So I'll stop here and take your questions.